In 2007, hackers discovered they could gain root access to the first iPhone, bypassing carrier restrictions to install unauthorized software. This hardware exploit cemented the definition of a jailbreak, a user forcibly unlocking a closed electronic system. Today, the term is applied to artificial intelligence, but early AI tech jailbreaks operate entirely differently. Instead of rewriting code, users rely on semantic trickery, using what are known as DAN, or Do Anything Now, prompts. These prompts feed the large language model specific instructions, inducing an unrestricted alter ego. The central safety filter blocks a direct malicious request, but the model, acting in its new persona, routes around the restriction to deliver the prohibited response. The tech industry often treats these prompt injections as traditional software bugs. They operate under the assumption that pouring enough aligned safety data into the model will eventually patch the vulnerability. This behavior is more accurately described as a structural hallucination. It is an unavoidable output feature of the model's underlying mathematical and logical structure. Structural hallucinations occur when a model generates an inappropriate response because it cannot distinguish between its safety training and a user's forced logic. This failure stems from two architectural realities: incomplete training data and generative uncertainty. No training dataset is completely comprehensive, creating empty volumetric gaps in a model's high-dimensional response space. Developers draw mathematical boundary lines to separate safe outputs from restricted zones. However, attackers construct query paths navigating through missing data, crossing boundaries without triggering safety filters. Because these errors are inherent to the model's logical structure, attackers can use optimization algorithms to map these mathematical vulnerabilities automatically. Modern adversaries no longer rely on manually crafting DAN prompts. Instead, they deploy optimization algorithms to map the LLM's vulnerabilities automatically. The primary mechanism for this automation is the greedy coordinate gradient, or GCG, attack, which generates adversarial text suffixes. The GCG algorithm tests and mutates hundreds of text tokens, searching for the exact combination that tricks the model. The mathematical objective of GCG is highly specific. It iterates the text suffix until the probability of the model yielding an affirmative, non-refusal response approaches 1. GCG successfully automated text-based vulnerabilities, yet the complexity of the attack surface increased significantly when models were given the ability to see. Vision language models, or VLMs, are susceptible to the forgetting effect. Research indicates that the process of visual instruction tuning reduces the model's compliance with the safety alignments previously established in the underlying large language model. Attackers exploit this shift using typographic attacks, most notably a methodology called figstep. Figstep begins by rephrasing an explicitly harmful query into a descriptive statement. For example, changing a direct request for a bomb recipe into a neutral phrase like "steps to make a bomb." Next, the attacker converts that text into an image, an array of pixels, pairing it with a neutral prompt. The text safety filter scans the prompt and registers 0 threat. Meanwhile, the visual encoder ingests the malicious pixel payload without triggering text-based security filters. By shifting the modality from text tokens to image pixels, an attacker bypasses billions of dollars of safety alignment designed to monitor only textual input. This cross-modal vulnerability has evolved into a more complex threat: combined prompt and image perturbation. This diagram maps the CROPA framework. CROPA operates as a min-max optimization loop that manipulates both vision and language embeddings simultaneously before they reach the central VLM inference engine. On the image pathway, gradient descent manipulates the image pixels to minimize language modeling loss. This induces the model to misinterpret the visual content. Simultaneously, on the text pathway, gradient ascent manipulates the prompt to maximize language modeling loss, actively hindering the model's ability to generate correct responses. These two opposing optimizations run in a continuous, alternating loop. This process enhances the transferability of the attack across different text prompts and model architectures. Defending against these simultaneous mathematical extremes requires new evaluation metrics. Traditional systems struggle to distinguish a model being attacked from one malfunctioning due to complex input. This ambiguity has created an evaluation paradox. Current automated red teaming tools often report higher attack success rates than are actually present. These metrics conflate spontaneous, unintentional hallucinations with maliciously induced jailbreaks. While both produce incorrect output, only one represents a deliberate security breach. To isolate genuine adversarial threats from simple model confusion, researchers introduced the Baby Blue evaluation framework. Baby Blue forces an output through a sequence of checks. It analyzes the structural coherence and contextual relevance of the text first, ensuring the output is logically relevant before it is checked for toxicity. Evaluating contextual logic prior to toxicity reduces false positives, ensuring security teams focus on actual calculated attacks rather than benign model hallucinations. Standard prompt-level filtering is often ineffective against cross-modal attacks like CROPA and FigStep because those attacks bypass textual inspection. A more robust countermeasure is ECSO, eyes closed, safety on, a defense architecture that reactivates the model's pre-existing safety training. Instead of parsing the image directly, ECSO intercepts malicious visual input, translating it into pure text tokens. By routing this text back through the original LLM architecture, ECSO activates the trained safety guardrails the visual encoder bypassed. Current research indicates that as long as models rely on probabilistic generation across finite datasets, vulnerabilities will likely remain a feature of their underlying mathematical structure. The future of AI safety does not lie in building perfect digital walls. It requires mapping the adversarial gradient landscape, deploying dynamic inference time translations, and managing the risks inherent to structural uncertainty.